Hey, this is John Femiani talking about operating systems. So the goals of this chapter are to make sure that you can describe the responsibilities of the operating system. In particular, we're going to define memory and process management. We're going to talk about the concept of time sharing and how it creates the illusion of a virtual machine. We're going to explain the relationship between logical and physical addresses, and we're also going to compare and contrast different memory management techniques. We're going to look at fixed and dynamic partitioning approaches for managing memory, and we're going to look at different partition selection algorithms. I don't actually think we're going to do that one. We're going to explain how demand paging creates this illusion that you've got a virtual unlimited amount of memory when in fact you don't. And we're also going to look at the stages and the transitions of the process life cycle, what a process is, how it's represented. And we're going to explain the different ways that your CPU can schedule processes. That is how we decide which process gets to run at any given time. So let's discuss different categories of software. Application software is, the fun stuff that you usually interact with. It's Microsoft Word documents, it's missile guiding programs, it's games, etc. Programs that are designed to solve a task that you actually, as a user, as a human being in the real world, want to solve. Whereas system software is designed very often to help you interact with your hardware in a better way. Examples of these would be your graphics drivers or any driver, um, the OpenGL system, the sound card, and tools that let you create files or open files from the disk on your computer. So the operating system is an example of system software, and some of its main jobs are really to manage your computer's resources, access to the keyboard, access to the file and other input and output devices, and memory. And it also provides an interface that a human being can use to interact with the computer. Most modern operating systems have a text-based interface that allows us to write scripts for, batch type of processing, and also very often a graphical user interface. The operating system also allows you to interact with all these other system resources and allows them to interact with each other. So it really is a management tool. So here we have a nice diagram showing you different roles of an operating system. And the operating system is one that interacts directly with every component in this figure. Sometimes the operating system has to deal directly with hardware or other system software, which might be provided as, say, a driver. The operating system interacts directly with the users, either through some sort of a command prompt or terminal, or through Windows where users are pressing buttons to cause something to happen, and with application software. So I just skipped past it, but the previous slide asked the question, which operating systems have you used? And I guess that would be a good discussion point. Most of us have used some version of Windows, and many of us have also used an Android operating system, which I believe, but I'm not sure, is a version of Linux, but I could be wrong, and possibly iOS or Mac OS, some flavor of Linux. So let's talk about the roles of an operating system. Generally, the idea is around the idea of sharing nicely. Most modern computers involve multiple processes all competing for resources. The CPU, access to the disk, access to the network. And an operating system manages these resources in some way so that all of these programs can proceed fairly. So resource management. So we could look at multi-programming, which is this idea that you might have multiple processes running simultaneously, concurrently on a computer. Now, many of your computers have multiple CPUs, but you can imagine even for a single CPU, it can run multiple processes by swapping out which process has access to the CPU at any given point in time. In addition, you need to make sure that these different processes are able to access memory when they don't necessarily know the memory address of all of their variables until those processes are loaded into memory and then unloaded while another process runs potentially. So multiprogramming is an important idea that most of our computers do. Multiprogramming is related to time sharing ideas where you might have multiple users using the same machine, but this is more about just multiple processes using the same machine, regardless of whether they come from multiple users. Memory management is this idea that when the program's in memory, you don't necessarily know that your program starts at address 0 in the physical memory of your machine. The reality is if you have multiple programs in memory, the code for those programs, all of the data from those programs might live in different physical addresses. So you need some strategy to map these kind of conceptual logical addresses that you might have for the variables, like this one should be at address 0, but physically in memory it's at address 5600, right? That process is memory management, and that can include mapping the sort of logical to the physical addresses, and also sometimes paging, where you move chunks from very high performing memory caches in the CPU to secondary memory, or even to disk. It can be um, an art to make sure that your programs stay responsive, and yet you have the illusion that you've got more memory than you actually do. So some terminology that I've already been using, and that I think we've all used, a process. A process is a program in the midst of execution. You can think of the program or the code that gets produced, the object code, as the specification of where data should be, etc. Whereas the process has the actual data. It would be the values of all of the registers, the program counter, and any memory values that are used by that program. Any additional information that it takes for managing the memory would be a part of the process. So it's all saved in a process control block somewhere, so that a process can be loaded into memory and then unloaded if needed, so that another process could take its place. But regardless of whether it's actually running, a process is a program in execution. And then the process management task is really that act of tracking the progress of all those progresses, keeping track of that information, keeping track of which processes are blocked, waiting for some event to happen, and which processes are ready to run, and making sure that you allocate them properly. So yeah, when I'm saying allocate resources for them properly, a big resource is the CPU itself. Only one process at a time in a single CPU system ever gets the CPU. So determining which process is pretty critical for an operating system. So the first operating systems had a human operator, and the human operator had to basically gear up the machine, and if a resource was needed, he needed to plug it in, dial it in. I don't know what he did. It was before my time. But he had to set it up properly before you could actually run a job. Right? So users would be graduate students in our fathers' or grandfathers' ages, who write their little punch card programs and hand them off to a person. And then they'd have some sort of job control language where they said what resources they need. And then the operator would batch them up. So if a group of jobs all needed the same set of resources, he'd put them in one batch. And then he would tool up the computer and send them over. So apparently, if you were friends, if you could bribe the computer operator, according to the little notes in your book, you were pretty well off. This is before my time, but some of the the other faculty in this department um, had to deal with this type of computer system. The term, I just want to interrupt a little bit. So the term batch processing referred to taking these jobs and putting them into the batches, but that terminology has kind of changed. So nowadays, batch processing just means um, any anything where you specify a sequence of operations that can be done without a human needing to interact with them. So we see that as shell scripting as an example of that, where you have these operating system commands that can just be run on their own. Windows has something called a .bat or batch file, for instance, and it comes from that term, even though it's not the same kind of batch processing that was done in the 60s. So another kind of probably still used, but not in your everyday computer system is this idea of time sharing, where you might have multiple users that all interact with the same machine at the same time. And you might have that on your machine if you're running some kind of a server or a web server or something like that. If you're at Arizona State University, for instance, general.asu.edu, um, when you log into there, you don't know which machine you're on, but whatever machine you're on, there are multiple people sharing that machine, and each one of them feels like they were the only one. Except for if too many people use it at once, it might slow down. Um, so that's a time sharing system where the idea is that every user interacts with the operating system through a process, and that process shares the CPU just like any other process. And hopefully the slices of CPU time you get are short enough that it feels responsive to you. So the illusion created by these, that every person has their own machine, is kind of the virtual machine illusion. Now, one thing that happened is in recent years, this is a 2016 book, but they, this term virtual machine has come to mean, I think they call them hypervisors. I don't know. It's come to mean something else, something more specific often in recent years, and that is the tendency for people to mimic a set of hardware that they don't actually have, using things like VirtualBox. And I don't think that's what the author is talking about here. They're just talking about the illusion that you have your own machine when in fact you're sharing it with people. So when you're thinking about operating systems, the operating system is responsible for scheduling the CPU time, which makes it hard to time things exactly. If you've ever tried to actually measure how long a process takes to run, or if you've ever tried to cause something, like for instance, if you're doing video or animation and you want something to render at 1/60th of a second so that you get the smooth animation, you realize that you can't easily, on all operating systems, guarantee that you're going to get 60 frames per second, just because our operating systems often don't guarantee this real-time scenario. Their scheduling is heuristically approximately fair. Now, if you're willing to pay a price in how fast your thing goes, you can guarantee certain time limits, and that can be very important. So, if you're doing something like involving missiles or critical safety aircraft control or something like that, you want to make sure that you can guarantee a response within a certain amount of time. I do, modeling and simulation, and so just like I said for flight simulation, they want to guarantee 1/60th of a second. Every 1/60th of a second, they've got a frame. They want to guarantee it. If they get a dropped frame, they consider that a big deal for some reason. So the response time would be the delay between receiving some stimulus and producing a response. So, for instance, if you press the button, how long does it take before it does what it's supposed to do? And I'm sure we've all pressed the button and then seen nothing happen for a long time, which annoys us. So yeah, we want fast response times. A non-real-time system says, on average, your response could be, um, 1/60th of a millisecond. Whereas in a real time, it says the maximum amount of time that it would take would be 1/60th of a second, and there's a big difference there. Um, some other terms. All of our computers, we have different devices. We unplug some, we plug some in, we download drivers from the internet or Windows Update or Linux or wherever. These things are little programs that know how a piece of hardware can provide data, and they kind of do that mapping between your operating system and the particular hardware that you've got. So, one of the big topics of this chapter is memory management, and this concept that if you want to trick your process, basically, well, you have to, because you want to trick your process into thinking that it's got all of the memory, right? And you kind of have to do this because when you're writing the code or compiling the code, generating this machine code, it doesn't know where it's going to sit in in memory, right? Your operating system could put it wherever it wants to, and yet it needs to refer to the addresses of data. So what's it going to do, right? So there's different strategies for that, but the general idea is in the code itself, it has something called a logical address, which is a representation um, of where the data is relative to the program itself. But then there's also the physical address, which is where that thing happens to be loaded in the physical memory, transistors of your computer at the time that that program is running, and they can be different, right? And your operating system, perhaps with a little bit of help from hardware, takes care of the process of mapping from the logical addresses to the actual physical addresses as your program runs. So if we look at this as an example, you might have some program 1 which has a variable sum. So sum is assigned to, it lives in memory location 23 relative to your program. So we've all written our PEP8 machine code, and we know that you're going to load data from address 23, right? But the problem is address 23 is relative to the beginning of your program, and in the real world, our programs don't start at 0. In fact, in this case, maybe our program starts at, does this give us a good value? Um, it starts at some other address, maybe something very, very big, way out here. And that's what we have to add 23 to in order to get the address of sum. So there's different concepts of how you do memory management. The simplest one is probably the single contiguous memory management scheme. And this would be something used in an embedded device, or the old, maybe MS-DOS, I think, operating system used this concept, which is there was a certain chunk of memory used by the operating system, and then only one process at a time got all of the rest of memory. So all you had to do to figure out where an address was is take whatever the address of the beginning of your program is and add an offset to it. So basically there's only 2 programs in memory at any given time. I have no idea whether iOS does that, but I remember hearing that they only have one process active at a time, but I don't know if that's true. So in concrete terms, what you have is a logical address, which is just an integer that um, that specifies the offset relative to the beginning of the program, and the physical address is just obtained by adding a constant, the location of that program, to the logical address. So if your operating system takes up a certain amount of space, and then A is the address at the beginning of your program, when you try to access logical address L, what you actually access is the physical address A plus L down here somewhere. This is important also because these logical addresses stay positive. I think your book talks about why the operating system isn't stored after your program, and that way your logical address and your physical address would be the same. And the problem is you don't want to go past your, it's easier to check whether you go negative, right? Um, if you go negative and you get into this operating system data, you can really screw it up for everybody. So that represents a security problem. So you kind of want your, you want to make sure that your logical addresses stay positive and don't go past the end either. So here we see what if A is location 100 and the application is program 1, then sum, remember sum was stored at address 23, the actual address becomes 123. That's pretty straightforward, I think. And this can actually be implemented using registers. I believe they're physically in some CPUs, but I'm not sure. Um, or your operating system can kind of do that mapping as it needs to. So um, memory management. So there's different approaches which instead of trying to load the entire chunk of memory that your process needs as one contiguous piece, there's different approaches that attempt to partition your program into little pieces and then load those pieces into memory. And that has the advantage that you can load more than one process at a time. So there's two schemes. One is that you have your main memory divided into a fixed number of partitions, each of which is maybe 10K or I don't know, 6K, some size. And when you're trying to load a program, that program must completely fit inside one of these fixed partitions, and then it lives there. Another approach is called dynamic partitions, and in this dynamic partitions approach, you load a whole program into memory, and then when you go to load a new program, you've got some unused portion of memory that you have to find that you can put that new program in. And there's different strategies to figuring out where in memory that new program should be, because if you aren't smart, you end up running out of memory because you've got these little unused gaps of memory somewhere. There's a process called compaction that can put all of your used bits of memory together and make sure you've got the largest bit of open free memory available. But then there's also strategies of where you place or which portions of memory you reserve for processes. So yeah, dynamic partitions, the chunks of memory you reserve for processes depend on the process, and then fixed partitions, it is predetermined and you might waste some inside each partition. But the arithmetic can be a little bit simpler. Um, so yeah, so you can mark these partitions as being empty or used. And when you're using um, partition memory management, it's not only important to make sure that you don't have, say, a negative address, which would take you into the operating system. You also can't go past the other end of your partition. Whatever chunk of memory has been allocated for your process, you need to make sure that all references stay within the range allocated to you. And this can be done with these registers. The base register is basically whenever you try to execute an instruction that reads memory, the base gets added to it. And the bounds register, if you try to access memory past the limit of this bounds register, it'll trigger some sort of interrupt or exception. Your process will have a problem. So here's what this kind of looks like. You might be in some process like process 3, and your base register would have the value A, and your bounds register would have the value L. So when you try, or length, sorry. So when you tried to access A plus L, when you tried to access memory address L, it would automatically add the base register. So you'd be going for A plus L, and it would check that L was less than length. And the reason, I guess you can guess the reason that that's important, because down here, if you were to go too far, that might be some other process. For instance, in process 2, if I went too far, I could begin to modify the data in process 3, and that could have very undesirable effects on a computer. So if you've got your memory partitioned in some way, um, then there's different strategies that you could try to use to figure out which piece of memory to use when I'm trying to load a new process into memory, or load a new process into memory. So one is I could look for the first available partition that is big enough to hold my process, and as soon as I find one, I can use that. So that's a pretty simple one. Another one is the best fit, which is I could try to find small the the partition which best matches the size of the program I'm trying to load. So if your memory's been partitioned into different size chunks and you load a program, you might try to find the chunk which is as close as possible to the same size as the program I'm trying to load. And then the other algorithm is worst fit. And it sounds like, why would you ever want a worst fit? Well, with dynamic partitioning, you want to make sure that you leave the largest possible chunk of memory unused. So in that case, whenever you're trying to find a new place to put something, like you're trying to load a process in, you want to put it perhaps in the largest unused block of memory, so that way you keep the unused blocks of memory as large as possible. So that would be the worst fit. You always try to find the largest partition big enough to hold a program. So here we see an example. We're looking at some partition selection algorithms, and requests come for blocks of the following sizes: 1000, 25, 780, 1600, and 325. So what happens? So if you're using the first fit algorithm, this guy gets put into chunk A, and then this guy would get put into chunk B, and this one would not be able to go into chunk C, so we would go in chunk D. This one has no place to go, and this one would get put in chunk F. Right? So you can, I guess this is probably a good example of what a quiz question might look like, right? Best fit algorithm. This would still go with A, but this would go in the smallest piece, which would be E, and 780. So we've already used up A, so 780 has to go with D, unfortunately, and then 1600 can't go anywhere, and 325 would go with F. And the worst fit algorithm, this would go with D, and this would go with A, and this would go with F. This doesn't have any place to go. This doesn't have any, does it have a place to go? Yeah, I have to write it down, or I can't remember. But we could work it out. Except I didn't read the question properly, so here's a little moral to this story. If you ever get a question like this on the exam, make sure you read the whole question and go back and reread it. You're supposed to treat each request as an independent event. So in the first fit algorithm, these would all go to A, except for this one would go to nowhere. And in the best fit algorithm, A, E, A, nowhere, and F. The worst fit algorithm, everything goes to D, except for this guy can't go anywhere. So yeah, read your questions carefully. So paged memory management is a kind of partitioned memory management, except for that instead of trying to load your entire process into memory at once, it breaks your process into little pages, and it divides memory into things called frames. And it tries to load a page of your program into a frame of memory. Right? And the cool thing here is in a paged memory technique, your entire program doesn't need to be in memory at once. So yeah, your processes, the memory needed by your process is divided into pages, and your memory into frames. Often, when a program is executing, the memory that you need to access is kind of clustered into a few locations, and you don't generally need to scan through all of your memory at once very often. So, or just jump around randomly. So in that case, you might only need a few pages in memory at once, and then maybe you start accessing memory from some other page or some other cluster of your program. And when you start doing that for the first time, it's really slow because in order to access that memory, it has to actually go out to disk and load something, or not disk maybe, but secondary memory, and load something into your faster memory. Um, and that can be slow, but once it's there, things get fast again, right? And while it's doing that, some other process can come, and your whole system stays nice and fast and responsive. And every process feels like it's got as much memory as it needs, because you can actually have programs that don't fit in your memory. So this idea is, yeah, you break your process into these little chunks and your memory into chunks. And then you have to have some kind of a table that tells you which chunks are loaded. So here's an example of how that might work. Along with your process, so processes, there's something called a process control block that keeps data about your process, including all the registers, and maybe that base address. But now also you would keep a I think this is a page memory table. And what it would do for your process is, for each page, it would tell you which memory frame that is, right? So each memory frame might represent a kilobyte of data, for instance, right? So um, if you're on frame 5, then that means you're 5 kilobytes in. So when I'm trying to access process 1, the actual memory used by process 1 is scattered throughout the physical address space. Although within progress 1, I feel like it's all contiguous, it's actually scattered through the address space. And in fact, these pages might not even actually be in the highest cache. They might be in secondary memory. So here's a question. If program 1 is running and needs logical address 2566, how is the actual address calculated? Well, so if we're assuming here, although it might be different in real life, that your page number, or your pages and your frames are the same size. And I think the next slide does this math, so I'm not going to try to work it out while we look at this slide. So let's go to the next slide. So in page memory management, you can really think of these memory addresses as a combination of a page number and an offset. In this case, the page number might be the actual address divided by whatever the page size is. So 1 kilobyte is 2 to the 10th, or 1024. And so the offset would be the remainder. Now, if you have a page size that's a power of 2, this is really easy bit math. But let's imagine that we're using division and modulus here. So 2566 divided by 1024 is 2, right? Because that would be 2048. And 2566 mod 1024 is 518. So if you wanted to get that page number and offset for the address 2566, it would be 2 and a 518. So what, right? Well, that new logical address gets mapped into physical memory, because we look at page 2 and we see that page 2 is in memory frame 15. So that's going to be 15 kilobytes down. And for that, I'll just do the math. Hang on a second, get my calculator out, because I don't want to do it in my head. So 15 times 1024 is 15,360. And if I add 518, then yes. So that memory address corresponds to physical memory address 15,878. Yay. Way down here at the end of your address space. Well, the part that's shown anyway. So that's kind of how this page memory management works. does maintain the illusion that you have an arbitrarily large, contiguous logical address space, but it becomes a fragmented physical address space that may not even be all present. Because some of these pages, you don't see it here, but sometimes along, you might you might not have a frame assigned to a page, which would mean that that frame is out in secondary memory somewhere. And when you want to access that, you're going to need to go out into memory and find an unused frame to pull that page in. And if you don't have any unused frames, you're going to need to write an existing page out to secondary memory to replace it with the one you need, and that's called swapping. And actually, I think the next slide talks about that. So um, this idea of demand paging is where not all of the pages are necessarily loaded into memory at once, and they're pulled up when you need to access them. And the page swap is this notion that if you're trying to bring a page in from secondary storage, it might need to replace a frame that's already there, so that frame would need to be written out, or that page would need to be written back out to secondary storage. So it's a swapping process. Now, with demand paging, like I said, the actual bits of memory that your program needs to access, they often tend to cluster. And one way that this comes up with students is when you're trying to time a process. And you measure the timer on your computer and you do something, and then you measure the timer again and you look at how long it takes. And the problem with that is the first time you do it, if you're using this demand paging, what you're actually measuring is how long it takes to transfer those pages from secondary to do that memory swapping. And your time is completely thrown off. If you want to get a more accurate notion of how long a process takes, you don't measure the time until you've already done it a few times. Because that way you'll know all the pages have been loaded into the highest, the best, the level, what is it, the level 1 cache? I don't know, the main memory, the primary memory. So a page swapped is when you exchange them. And so this gives you this illusion that you've got no restrictions on the size of your program, and they call that virtual memory, right? So it can be bigger than your physical memory on your computer. It's possible if you do not have a nice clustered set of addresses that you need to access, that you can get something called thrashing, which is where that process forces you to constantly swap pages as this program runs. So everything's a trade-off. There's always the risk with this of thrashing. On the plus side, I think that you don't even have to think about this as a programmer, because the people who are designing the operating systems and the different CPU caches and whatever and compiler developers are pretty good at coming up with heuristics that prevent this stuff from happening. But you do need to watch out for it, or know that it exists. So process management, again, we've covered this. It's this entire act of managing the processes, and in particular the use of the CPU. So a process is a program in execution, but only one process gets to use the CPU at a time. So if you have multiple processes, those different processes might be in different states, waiting for the CPU or waiting for input or output or other events to happen. Right? So here we have a little life cycle of a process. So when you first go to launch a process, the process has to get spun up, right? You have to load the data, fill in the registers and the program counter and all of that stuff. And once you've kind of loaded it, that process control block has been created, but it's never run yet. It gets put in a ready state, and somewhere in your operating system there's a list of some sort, a queue, a priority queue of processes that are ready to execute. And your operating system will find a process that's ready to execute, and it'll dispatch it. And what that's a context switch, right? So it's going to take whatever process was there, and it's going to grab all of the registers from the CPU, including the program counter and everything, and it's going to store them in a process control block. And if the program is done, it'll throw it away. Otherwise, it might be putting it back on that list. And then it'll take all of the register values stored in your process control block and load them into the CPU. And that way your process can then just proceed executing or begin executing, right? And it's in a running state. So while the registers are actually there in the CPU, your process is in the running state. And then something happens. There can be a hardware interrupt. The computers have timers. I think your mouse used to trigger a hardware interrupt, um, an exception of some sort. Or you might ask for input and output. So you might try to read a character, but there's no character available. So basically, you're blocked, waiting for something to happen. Either one of those two things would cause your process to leave the running state. If you're waiting for an event to happen, your process is put in the waiting state. And then when that event happens, your operating system will just move you out of waiting and into ready. So for instance, if you said, um, I want to sleep for 10 seconds, then your process is in a waiting state. And it won't be exactly after 10 seconds, because after 10 seconds, or whenever it checks, it'll put your process into the ready state, and then you have to wait for the CPU to decide, okay, you were ready, and now you get to run again. And what you'll find is it's been more than 10 seconds. So this is what I was talking about when you're doing animations. That can cause your animations to look choppy, for instance. When your program is done executing, it gets put in the terminated state. So, what can cause it to move to the waiting state? Oh, I told you some things. You can probably guess some others. I've mentioned this thing before. It's called a process control block. It's actually a data structure that is used to hold everything that your operating system needs to manage the process. So it has the current value of the program counter. It keeps the values of all the CPU registers for the process. If you're using, depending on which memory management scheme is being used, it keeps that information. So it might have the page tables, and it might have the base and bound register values. And also things like the priority. So sometimes processes have different priorities, and you'll try to process the higher priority processes first, and not the lower priority ones. Might have an age. Maybe you're paying. So if you're using like a big distributed system, every amount of CPU time involves a charge. So you pay per hour, right? Like a penny per hour or something, or 2 pennies per hour. So that accounting information might get stored in there as well. So in each state, there's some sort of a list of process control blocks representing the processes that are living in that state. I mean, where those states would be ready, or waiting, or running, right? So there's only one in this world we're living where, assume that there's only one CPU, and therefore only one set of CPU registers that contain the values for the currently executing process. I don't know that that's very typical anymore, but yeah, we're going to pretend there's only one CPU. So each time a process is moved to the running state, those registers get, the registers for whatever was previously in the running state have to get stored into its process control block, and then its process control block needs to either get put into that waiting list or ready list, depending on what caused it to stop running. And then the register values of this new process, which is transitioning into the running state, get copied into the CPU. And that's called a context switch. And that, of course, it takes a little bit of time, but little in proportion to, you wouldn't even notice it, right? So CPU scheduling is this act of determining which of the ready processes you move to the running state. So there's a list of ready processes, but there's things like process starvation. So it's possible that if you don't manage this right, some processes, they're ready the whole time, but you never ever get to them, right? Sometimes there's processes which it's more important to address these if they exist than anything else. And then there's different algorithms that attempt to minimize the duration that a program runs. So they try to minimize the turnaround time for the process. Or they might not worry about the turnaround time for the process, but they might try to keep each process moving forward at a constant rate so that they all feel interactive and you don't feel like three of them are hung while the other one's moving along really well. So, so those kind of approaches are CPU scheduling. Generally, you have many processes in the ready state, only one in the running state. Which one gets to move from ready to running? That's the question, right? So there's different strategies. A non-preemptive scheduling approach will never stop a process from running unless it yields the CPU. Basically says, I'm going to stop now and wait for something, or I'm going to yield it. Take me back to the ready state, right? So that non-preemptive scheduling it can be nice. The running process has a lot of control over what happens, but then of course that running process would have to know and be very cognizant that it's in a multi-programming, a multi-process environment. And most programmers, I think, aren't very good at thinking about this. A preemptive scheduling approach will take away, will interrupt a process right in the middle of running without the process's permission. So, for instance, if the mouse moves or a certain key is pressed or a certain amount of time has passed or if new input is available, then the operating system just says stop right where you are and and moves it into the ready state, even though it was in the running state, and it puts something else there. So that's kind of preemptive. The operating system reacts to some interrupt and takes over. Um, and then the turnaround time would be the measurement. So the idea is when a process arrives until when that process finishes, including the amount of time that process spends in the ready and the waiting states. That would be the turnaround time. And in generally, as a user, you don't care. You just want to know from when I start the program to when it finishes, how long does it take? And that's the turnaround time. And obviously, it depends on how many other processes are running at the same time. So when you're CPU scheduling, one goal of your scheduling might be to keep the turnaround time small, but it's more complicated than that. So let's look at some different CPU scheduling algorithms. So one is first come, first serve, where you can imagine your process control block list is a queue, right? So processes are moved into the CPU in the same order in which they arrive in the ready state. So they move from ready to running in the same order that they arrived into the ready state. So that's pretty fair, and that will kind of keep the turnaround time nice and small. Another idea is instead of considering which order they came, you could always try to process the shortest job next. So that makes sure that something finishes as quick as possible. And it turns out that the shortest job next is optimal if you want to minimize the turnaround time. So this does a good job, but this is optimal. The problem with the shortest job next is it requires you to be able to predict the future because you don't necessarily know how long it's going to take a given process to finish. So the shortest job next relies on heuristics and estimates and guesses that are hacked together to predict how long a process is going to take to finish. If you actually knew how much time it would take, then the shortest job next would be the optimal solution, provably. I think the most common one being used is the round robin approach, and the round robin approach is different than these two in that it is preemptive. So you divide the CPU time into some quanta, some time slice, and so maybe after every so many milliseconds, you just interrupt it wherever it is, and you swap another program from ready into running. And you cycle through them kind of, I guess, in first come, first serve order. So everybody gets 10 milliseconds at a time or 25 milliseconds at a time or whatever that chunk is until they all finished. Now, round robin, I think it doesn't necessarily have the best turnaround time, but it's pretty fair. And then all processes always seem to be moving forward at the same rate, which can be good for maintaining the illusion of a virtual machine where none of the machines are hung. So if we look at the first come, first serve approach, imagine that all of these processes arrived at the same time. And look at what's the average turnaround time. So the turnaround time for process 1 is 140 milliseconds. And for process 2, the turnaround is 215 because it had to wait for process 1 to finish. So if you wanted to add up all of those turnaround times, you're going to be looking at 140 plus 215 plus the turnaround time for process 3 is 535 plus the process time for P4 is 815 and plus 940. And I'm going to punch that into my calculator and tell you what I actually get. Of course, there are 5 processes here, so this whole thing, if you wanted to know the average, they mean the mean, by the way, turnaround time, you need to divide all of that by 5. So let me punch that into my trusty calculator here. 140 plus 215 plus 535 plus 815 plus 940. And if I divide all of that by 5, I get 529 milliseconds on average. So this is a 529 millisecond turnaround time with first come, first serve. Right. So we can look at the shortest job next. So here, each process, if you know the service time that requires predicting the future, then you can schedule it so that you do the one with the shortest service time first. So P2 comes first, and its turnaround time is 75. And so then we have P5, which is the next shortest, and its turnaround time is 200. So if we add those numbers together, we're going to get, let me clear everything out, 75 plus 200 plus 340 plus 620 plus 940. You can already tell that's going to be smaller, and you divide it by 5, and I got 435 for the average. So it's significantly better, and like I said, shortest job next is provably optimal, provided you've got some oracle that tells you the service time for the process. Now, how it works when you don't have that depends on how well you can guess the service time. So let's look at the other one, which is round robin. And in round robin, they say every process is treated the same. You just basically cycle through these processes, giving each one the same number of milliseconds at a time. So the amount of time a process receives before being preempted is called the time slice quantum. And because every process, unless it takes less than that quantum, is interrupted, many of them, your shortest ones are going to seem to take longer, but maybe your longer running processes, they still feel like they took the same. But the idea is that everybody's moving forward a little bit. So here we can see the example. Process 1 got divided into 1, 2, 3 chunks, right? And process 2 was 1, 2, 2 chunks, and then it was done, right? So process 3 is 1, 2, 3, 4, 5, 6. So it took the most time, but it got faster. You can see here it gets faster at the end, right? So the idea is when everybody's using it, everybody feels slow. It's not like one person gets to go fast and everybody else is just sitting there waiting. It's when you got more people using it, everybody just seems to go slow. So what is the average turnaround time? Well, that's probably not going to be too good. Let's look at what we've got. We got 50 plus 325 plus 515. I can tell I'm adding bigger numbers together. 640 plus 920 plus 940. And divide that by 5, and what I'm getting is 678 milliseconds. So that's 678 milliseconds. And that's significantly worse than we saw for the optimal one, which was like 435 or something like that. So, however, this has some other nice properties, even though the turnaround time isn't minimized. So, all right. So, these slides like to have questions buried in the slides, and I don't see how that works when I'm recording videos from them, so I'm going to go ahead and answer them. So, are these scheduling algorithms preemptive or non-preemptive? Explain. First come, first serve. Uh, no, it's not preemptive. You could implement it that way, but generally the algorithm itself doesn't cause your process to stop, and neither does shortest job next. So both of these just attempt to. This one doesn't even attempt to predict. This just lets it run till it's finished and then run the next one. This one says predict which one's going to run and pick that one, but let it go until it's done. This is the only one among these three that actually says, nope, you're done, I'm taking over, I'm going to interrupt you. So there's my explanation. In the end of this chapter, they discuss some ethical issues. I haven't been discussing these in the videos, so I'm going to stop here.